Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And in this playlist, we're creating little mini-series that correspond to the different experimental designs. And this one is a balanced two-factor factorial design without interaction. This is part one of a 7-part series. The first one I'm calling Model Development. Now, the experiment involves two factors to study. Each factor level occurs within the other factor levels. A simple example is a balanced two-factor factorial design. Factor A has A levels, factor B has B levels, and there's N replicates at each combination of the levels. So maybe a simple example would be this. If we're studying crop yield, and maybe factor A is the amount of fertilizer that's applied to this plot, and this would be the amount of weed control applied to this plot. And then they look at yield growth in this plot of land. And that's perhaps a simple example, but the idea with factorial is that each level occurs within the other. So notice that this is the level 1 of fertilizer, for example, and it's combined with each level of weed control. The next level is combined with each level of B. So every level of A is combined with level of B. And then you can have N replicates within each level. Okay, so the without interaction means we're in what's called a two-way additive model, which is this. So Yij is equal to mu plus alpha I plus beta j plus epsilon ij k. So I goes from 1 to A, that's how many levels of factor A. J goes from 1 to B, and that's how many levels of factor B. K is the number of replicates within each of the level combinations. So Yijk equals the response for the ith level of A, the jth level of B, and the kth replicate. Mu, alphas, and betas are unknown fixed parameters, at least for now. Epsilon, the error term, is IID normal, mean zero, constant variance sigma squared. And the expected value of a combination, so the ijth combination, would just be mu plus alpha I plus beta j. And generically we call that mu ij, right? So if we take the expected value of this is 0, so then those stay. And that's for every replicate. So if you're in here, the expected value is constant. That's what this is saying. Now, one of the features of an additive model is what this next topic deals with. And it really starts here but continues to page 2. If we were to plot these, or table these population means, so each one of these, so the mean of 1, 1, so that's factor level 1, A1 and B1, and this is mu 1, 2, etc. So basically we're tabling the population means for each cell, or each factor level combination. And then now let's plot these. So the way we plot these, and we're assuming a two-way additive model. So we have each level across the x-axis, and then for each level we plot all the means for the b's, and then we do that for each level. But then within each level we join them with a line. And one of the features of this is that all the lines are parallel-ish. And I'll show you what that means. In an additive model, let me state this and then I'll go here. The effect of a factor level in A is constant within the factor levels of B. And so what that means is if we're in factor level, A1, the first level of factor A, they each have an effect, but notice that it's the same effect. So to go from, you know, B1 to B2, it's this distance, which would be alpha 1, and it's this distance for going from B2 to B3. Now, the ish means that these are not perfectly level, because maybe oh, my cat wants out. It's driving me crazy. For factor level A2, the effect may be different. So the effect here is not the same as here. So all of these may be less, right? So if it's less, these lines can't be perfectly parallel because the gap would have to be the same. But the idea of additive model is going between the levels of B within A2 is constant, and that occurs with each level. So in practice, we'll never know the exact population means, right? We just can't. So what we do is we estimate this previous plot with the sample means. So if we were table that, then all the observations in A1, B1, we just add them up and divide by how many there are. In this case, there's n. And the notation we're going to use is y11.bar. Now, remember, y has 3 indexes, I, j, and k. And whenever there's a dot, it means we add up over that index. So, for instance, yij dot means we're summing over the kth index. Now, if we put a bar above it, it means we've added up the kth index over the kth index, but that bar means we divide by how many there are, so which is this. And technically, since this is the sum, then I could divide by n, and all 3 of these are the same. Sometimes it's easier for me to think about it like this, and then sometimes it's easier for me to think about it like this. So that's why I'm doing both. But once you come up with these sample means, then we can plot the sample means and see if all the lines are parallel-ish. Now, the model in matrix form is this: y equal x beta plus epsilon. So it is a linear model. The error term is multivariate normal, mean vector 0, variance covariance matrix sigma squared I. Now, in here, so there's A levels of factor A, B levels of factor B, and there's n replicates within each of those. So the total number of observations we have is A times B times n. And then, of course, y is a vector, so it has column dimension 1. Beta is dimension 1 plus A plus B by 1. X is ABN, right? They are the same dimensions, has to be. And the columns is 1 plus A plus B. And the B deals with the factor B effect. A is, how many levels of factor A, and then 1 for the constant mu. Now, if we were to write this, kind of expand this or separate it into the different column spaces. So this one deals with the mu, x sigma deals with how many levels there are of factor A, x beta deals with how many levels of factor B, and you could multiply this out and get this. Now on the next page, I'm going to write all this out in detail, but it took up the whole page, so it has to be its own page. And that's the last page for this video. Alpha here, it's A by 1, right? There's A levels. B is B by 1. XA is, has to be the same dimension, same number of rows, so it's ABN. But there's A columns because it deals with alpha. And XB is ABN by B. Now here's how you'd write it out. So Y, it's one long vector, but the convention is that factor A comes first, and then the factor B, and then the number of replicates, right? So all of these here deal with factor level A1. So this big group. And then what comes next is factor level B1. So all of these deal with B1, and then these are the number of replicates from 1 to n. So this is B2, and then the number of replicates, and that continues to the bth level of factor B, and then these are the replicates. Now, and then it continues. So this is factor level A2, and that's, you list them all right in a row, and then within that you go factor level B1, and then the replicates, B2, and then the replicates, all the way to, you know, the level B of factor B, and all the replicates. And then you just keep going, and then you end up with factor level A, right? And then it's B, and then it's the replicate. So this is it. And the way we do this though is, here is the beta parameters. So that's mu, alpha 1, alpha 2, all the way to alpha A, B1, B2, all the way to BB, and then, or beta B. But the key is, when you matrix multiply this, you want to make sure that you're picking off the right ones. So now this matrix here, I originally had, wherever there's a 1, there's a 1. So this is a 1 vector, this is a 1 vector, this is a 1 vector, 1 vector, and the rest are zeros. And originally I put in zeros, but didn't really come across well in this video. Maybe on like a chalkboard or a whiteboard, it would look better, but I didn't like it here. So now let's look at this. So if this is y111, so when we multiply this over, we want to pick off the mu, because that has to be the case in every one. And that's why it's one big long 1 vector, because every time we do this multiplication, we pick off that mu. And then here, so it's treatment 1, right? So we want to make sure to pick off alpha 1. And notice when we do this multiplication, we always pick it off for treatment level 1, all the way down. And then once we get to treatment level, you know, A2, then these have to be zeros, and then the 1 vector moves over corresponding to B. So that way when we take this multiplication, we're picking off alpha 2, which corresponds with the second level of A. Now here, this deals with the factor B, and we want to make sure to pick off the right one. So this first one is factor B1. So when we do this multiplication, this one here is picking off this B1. And notice that there's in replications, right? And that deals with, you know, each rep, you know, so it's the same. So this is going to pick off mu, A1, B1. But now when we get to B2, we're still in treatment 1. So that's why there's a 1 vector here. Everything else is 0. But here we want beta 2, so we have to move over 1. So when we do this multiplication, it picks off beta 2. And then there's in replicates. So then we just keep going, and then we get to the 8th or the bth level of B, which will pick off this one. And then we repeat. So right, and then now this is treatment A, and then this is B1, beta 2, you know, not B, and then the bth level. So then it just, everything repeats until we get to the end. Okay, well, hopefully that was informative. This is just part 1 of a 7-part series on balanced 2-factor factorial designs. Oh, the word balanced means that there's the same number of replicates in each level combination. So there's n replicates at each level. That's what balanced means. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.